Okay, so far. Okay, guys. Now, so far on last day in the last lecture, we have studied the definition of acid and bases, Bronsted Lowry, right, Arrhenius, etc. And we reach out to the equilibrium also, but we have touched a few point on that. Okay, so we discuss about the what is the strong acid, what is the strong base, etc. However, in some small extent, but today we will again study the conjugate base pair, reactions of acid and bases, etc. Okay, let's go. So last time also we have discussed about the conjugate acid and base pairs. Okay, so now let's see, first of all, let's take that from the example. Okay, so what is that? S2S, you see, let me go there. Okay, so S2S plus NS3 gives you HS minus plus NS4. Okay, so S2S, look at that very carefully. NS3 gives you HS minus plus NS4 plus. So always the minus, they can accept the hydrogen, right? They can accept the proton. That's why this guy is base, right? It is plus, this can donate the hydrogen because it is NS4 plus, so it can give one hydrogen. That's why it is acid. So here also you know that NS3 is base and this guy is acid. Okay, so if there is acid in the right hand side and base in the right hand side, these two are conjugates of each other. Or this is the acid is S2S, and HS minus is conjugate base of S2S. This is a pair, right? Now let's see the another pair. Let me take the another color for that another pair. So another pair is this pair, right? So if you see that this pair is base is NS3 and NS4 plus, it is an conjugate acid of NS3. So these are said to be the conjugate acid base pairs, right? So you see, this is acid, this is conjugate base, this is acid, this is conjugate base, and this is base and this is conjugate acid. Okay, so now NS3 accept the S plus and become the NS4 plus, and S2 HS minus accept the S plus and the S2S become the acid. So that's why these are conjugate acid base pair. But what happening here, look at that, S2S and it has HS. One H is missing here, right? So it has two H and it has one S. Okay, base NS3 is here, one H is added here. So if acid lose H plus, it become whatever that is conjugate base. And if base and gain H plus, whatever that is conjugate acid. Okay, so NS3 accept H plus, so NS4 plus, so this is the base and it get H plus, add one H plus and then it will be NH4 plus, and that is the conjugate acid. Remove one H from H2S and then HS minus, this is a conjugate base. Okay, now hope you understand what are the conjugate acid base pair. Okay, now let's see some example here. In that reaction, what are the conjugate acid base pair? Okay, so HF plus S2O, look at that. HF, what will be its conjugate base? Remove one H. Okay, this is HF, right? What will be its conjugate base? Remove one H and what remains? F minus is, see, conjugate base is F minus plus. And if that is the base, add one H plus, okay, add additional S plus, and what becomes that is the acid, S3O plus. Similarly HCOS, right, remove one H and what is that? CHCOO, see, HCOO, then that is the base, and here Cn minus is the base, and add that H plus here and it become HCl, like all of them. As SPO4 HPO4 2 minus, so remove H plus, then PO4 3 is the base, 3 minus is the base, and add that H to the SO3 2 minus, and HSO3 is the acid. So in this way we can find the conjugate acid base pair of a reaction. Okay, so let's go to the further. So now look at that, some example, hydroiodic acid, hydrochloric acid, H2SO4, lots of acid. Okay, so whatever these are the weak acids, these, and whatever those up one, they are strong. H2O is stronger than acetic acid is stronger, SPO4 is 2 minus is stronger than water, SCO3 is stronger than HPO4 2 minus, right? And hexanol is stronger than SCO3 minus, then hydrogen cyanide is stronger than, like that. HCl is stronger than H2SO4. Strongest is Hi, right? So strong means which can dissociate 100%. Which is more, if Ka, you see, remember that Ka and Kb, right? So which has more Ka, that is more stronger we have. So it's a conjugate base are these, and we have already seen this chart also in the previous case. So let's say identify the conjugate acid base pairs in the following reaction. H2O SO3 2 minus, look at that, which is acid and which is base. This is minus, see, minus means that it is all base. But the H2O can be base and acid, base, acid both, right? So SO3 is base, it means that it is not base, it is acid. H2O is acid, it is base. So acid, if you remove one hydrogen, it become conjugate base. Now see, H2O has 2 hydrogen, remove 1 hydrogen, OH minus conjugate base, and add 1 hydrogen here. If additional hydrogen you will put here, then that will be the conjugate acid. This is your conjugate acid. Done. Similarly there also, down also. Good. Now let's go further. So this one also we already have studied in the previous slide also, right? See, acid dissociation constant, base dissociation constant. In the acid, if the acid dissociation constant Ka is greater than, smaller than 1, that is weak acid. Okay, if Ka is greater than 1, very large, then that is strong acid. Similarly base, weak base, if Kb is, see, Kb is greater than 1, that is very large. If that is a strong base, less than is strong weak base. So we have already studied that. Okay, which is larger? If Kb1 is greater than Kb2, then B1 is the stronger base than B2, and similarly acid also. Good. If you have any question on this, you can ask me. Okay, so now curved arrow also, if you remember the curved arrow, what the curved arrow has bottom, this is the arrow, right? Bottom means where electron generate, and arrow is where electron goes. So in this case, look at that here, nitrogen has 1 lone pair, right? So this is the different molecule. Okay, acetic acid this is, okay, and this is the ammonia. Now ammonia has lone pair, acetic acid, this oxygen has also lone pair. What is happened is, so first of all, this nitrogen has 2 lone pair, right? So this OH, first of all, this OH, it has 2, let me write 2 electron here. These 2 electron added with that. Okay, so these both electrons accumulate with that oxygen, means these electrons go from here to here, and it become 1 2 3 lone pair, means 2 lone pair should be here, but it has 2, that's why what 1 minus, because this 1 electron, this oxygen already it has, and additional electron also it will go there, that's why additional electron means minus, right? This is minus. Plus, look at that, if this happens, then hydrogen don't have any electron, hydrogen electron deficient, that's why there is this nitrogen has a lone pair, that's why it can share with that hydrogen, and it can make this complex at NS4 plus this. So this is the ammonium ion, acetate ion. So the arrow pushing goes nitrogen. First of all, what happens first? That's most important, right? What happens first? This has 2 electrons, and this happens first. After this happens, this hydrogen liberates as a H plus, and this H plus grabbed by this nitrogen, and this one electron is share with that. Actually happening is this. Okay, so let me, the better example is, there are one electron is hydrogen, one electron with oxygen, right? Oxygen pulls that electron, this arrow here means that this electron goes to here. That's why oxygen has 1 minus. Done. Oxygen has one additional electron. There are two, right? It has one, but it becomes 2. That's why it is 1 minus. What happens this? Once this electron is pulled by oxygen, then hydrogen liberates as a H plus, and this nitrogen grabs H plus. How it grabs? This has one electron, and other electron it will share here. So now it has a bond here. So that's why a new bond is formed, NS bond. So this is the curved arrow, or this is arrow pushing also, it is, we say that. Now let's see the acid base equilibria. We know HCl is the strong acid, which means that the position of this equilibrium lies very far from the right. Okay. In contrast, acetic acid is a weak acid, and the position of the equilibrium lies very far to the left, because it's very weak, right? That's why equilibrium position lies to the left, right? Always it tries. You see, forward direction only this much, this much dissociate, right? See, small, right? But the backward is that much. It's saying this. Okay, so forward is that much, but the backward is this much. Okay. So you can see that forward is this much, but the backward rate is that much. It means that the almost acetic acid 95% don't dissociate, but 5% dissociate, means the equilibrium is always at the left, means the where is the product is. But in this case, all dissociate, everything dissociate, 100% dissociate. That's why it is a equilibrium at the right. So, but what if the base is not water? In case of this is the acid, this is the base. But if the not water, what happens? This is what will happen. That the equilibrium, it is the equilibrium. Either it may shift right or it may shift left in that scenario. Okay. So that's why both rates are same. In that case both rates are same. Now again, to predict the position of an acid base equilibrium such as this, we do the following. Now identify the two acids in the equilibrium, one on the left hand side and one on the right hand side. So if you go to the previous one, right, previous slide, we see that identify the which is base and which is acid in the left and right. Now in this case, I will instantly I will recognize this is the base, because this is a negative in charge, and this is the acid because it is positively charged, H plus, right? So now here which has hydrogen is the acid. That's why this will be acid, this is base. So first of all, this says that identify, we have identified, right? Using the information table A or table 1.5, determine which is the stronger acid and which is the weaker acid. Out of them, we have to go to the table here, which is the stronger and which is the weaker. So now, so we have to identify that. So, okay. So using that, for example, this is weak, NH3 is also weak, this is weak, this is weak. Okay. So we identify that. So remember that stronger acid gives you the weaker conjugate. Stronger acid gives you the weak conjugate, and the stronger base gives you the weak conjugate. Both strong always gives the weak conjugate. The stronger acid react with the stronger base to give the weaker acid, and weaker base and weaker acid and weaker base, and the equilibrium lies on the side of the weaker acid and the weaker base. So what it is saying that the stronger acid, so stronger acid react with stronger base. So if it is acid plus base and this is the stronger, this is stronger, this is stronger base. Okay, gives you the, okay, remember that the stronger acid being and which is the weaker base. Okay, and stronger acid react with the stronger base to give the weaker acid and the weaker base. So this gives weaker acid plus weak base. So this is the base. It also gives the acid plus base. So this is the weak acid, this is weak base. We have to remember that first of all, if the acid is stronger and base is stronger, then this gives the acid base, but weak and weak. So, and in that scenario, equilibrium lies on the side of the weaker. So where the weaker one, the left hand side is the weaker, right? That's why equilibrium always lies in the side of the weaker ones. So for example, let's say strong acid plus weak base gives you strong base, strong acid, then it will shift here because it weaker is here. So always equilibrium on the side of the weaker. So now let's see, identify the two acid and bases and their relatives. Now first of all, so acetic acid CH3COOH, acetic acid plus NH3 gives you CH3COO minus plus NH4 plus. Okay, so now first of all identify the acids or base. So position of this equilibrium lies to the right. So why? Look at that. So acetic acid, and this is the ammonia, and this is acetate ion, and this is ammonium ion. So this is also acid, this is base, this is base, this is acid. Now let's see that which is stronger than which is. Okay, let's go to here. So now search CH3COOH. Where is CH3? Now CH3COOH, this is here, CH3COOH. What is the acid here? NH4 plus. Where is the NH4 plus? NH4 plus. This is the NH4 plus. See these are stronger, right? Which is stronger? CH3COOH is stronger, right? That's why this is strong acid and this guy is weak acid. Stronger, I will say, not strong, but okay guys, I will say the stronger. Okay, let me see that. So I will say stronger. It's not strong acid, right? It is organic, that's why it's stronger. It is stronger than NH4 plus, so a stronger acid. And but this acid is, now let me take the another color, okay, for to write the board. Okay, so this actually may be better. So now let me write that. So stronger acid. So this acid is the stronger acid, and its conjugate here is its counterpart acid is weaker acid. Okay, now let's the base comparison NH3 and CH3CO. Let me take another color for that guy. This color, I like this color. That's good. Now NH3, where is NH3? You have to see NH3 in this side. Look at that. Down stronger. So NH3, and what is another? What is CH3CO minus? CH3CO minus. See, this is CH3CO minus weaker than NH3. This is again stronger base, and this guy is weaker base, right? So it means that this reaction is happening strong acid plus strong base giving you weak acid, weak base. So in that scenario, strong if it gives the weak, that's the favorable condition. So that's the favorable condition, means it can give the product. Stronger gives a weak. Then it is a favorable condition. That's why equilibrium in the right means that product will form. It means that. Okay. So very interesting, right? So remember that stronger gives the weaker is the best. So stronger gives the weaker is the favorable condition. So now, so here what will happen in this case? We find that, right? So the position of this equilibrium lies to the right, on the side of the weaker acid and weaker. Now here this is NH3, again the CH3CO minus NH4. So right hand side is longer, you see, right hand side is longer, right? Means about 95% is in the right hand side, means 95% it will convert CH3COOS plus NH3 into these two, only 5% return back. It means that, right, equilibrium shifted in the right hand side. So in this case, let's go further. Again, now predict the position of the equilibrium. Again same here, to position of the equilibrium we have to locate again. Okay, locate the stronger H2CO3 plus OH minus gives HCO3 minus plus H2O. This is the base, because it's minus charge. This is also base. This means it is acid. This means acid. So now let's see the chart again. If you see the chart again, okay, if you see the chart, so what the chart says is, now acid compare acid, okay, H2O, H3O, H2CO3, is there H2CO3, yeah, H2CO3, the carbonic acid. So this is, and water, where is the water? Maybe very down, right? See, water is weak, very weak acid. That's why this is strong and this is weak. We have compared the acid. Now compare the base, OH minus and HCO3 minus. Now let's go to the base side. OH minus, this is here, it is stronger, right? OH minus is stronger, only C2H5O minus is stronger than this. All others are weaker than OH minus. That's why this is strong, this is weak. Look at this equilibrium. Shift to the right, of course, shift to the right. So now the acid ionization constant. Now let's say ionization constant Ka, this is also said to be the Kc. Already we have discussed about that, product by reactant, right? Acid ionization constant is, we have already discussed that, and Kc less than 1, reaction proceed backward, Kc greater than 1, reaction proceed forward, and that we have already discussed. So now let's see some sample problem. Predicting the net direction of the acid base. Okay, we will predict the direction of acid base. H3PO4 minus NH3 gives you NH4 plus H3. Now look at that. I have already written here. This is stronger acid than this is weaker acid. H3PO4 minus is stronger than HPO4 2 minus. So weaker. This is strong. This is weak. Now NH3 is weaker base than NH4 plus. No. So just the opposite. Okay guys, here let me, so this is the weaker acid, right? It can donate the hydrogen. This is base, sorry, right? So now NH3 is stronger than HPO4 2 minus, and H3 this is base, right? Oh no, this is acid, sorry, this is acid, guys, this is acid. H3PO4 is acid, HPO4 2 minus is base. That's fine now. So this is stronger than this one, and that is stronger. So strong gives you weak. So that's why it is Kc will be greater than 1. So in this case, H2O plus HS minus OH minus H2S, I think we have done that also. Weaker acid, weaker base gives you stronger acid, stronger base. That's why reaction shifted to the left hand side, and Kc is less than 1 then. Reaction constant Kc will be less than 1. So here are the same examples here, same the chart is here. So Kc is same, acid dissociation constant or equilibrium constant or acid dissociation constant. So Kc greater than 1 means stronger, right? So strong gives you weak, and that scenario Kc is greater than 1. But the weak stronger gives the weak is obtained from stronger, then that is Kc is less than 1. So this is the simply chart, we have already have that in previously. So now let's see some constant. Acetic acid is this, Ka1 is 10 to the minus 5. See, these all have the carbon, right? These all are the weak acids, because look at that, Ka 10 to the minus 4, 10 to the minus 5, they are less than 1. So that's why they all are the weak acids. But the sum has one Ka1, no, okay, look at that, okay, HCl, let's dissociate that. It dissociates and it becomes H plus H3O plus Cl minus. And what is that? Ka1. And but H2SO4, that dissociates, it becomes HSO4 minus plus H3O plus. So this is K1. But this HSO4 also can further dissociate, which is H3O plus SO4 2 minus. This is K2. There are two Ks. First hydrogen dissociates, first dissociation constant. Then other second one also dissociates, second dissociation constant. That's why how many proton, that many dissociation constant. S3PO4 for example, S3PO4, it may have 3, look at that. Okay, S3 arsenic, okay, arsenic acid, see, there are 3 protons, that's why you have 3 Ka, Ka1, Ka2, Ka. Always you will see that K1 is the largest. First hydrogen release is the strongest, look at that, it is 10 to the minus 4, then Ka2 is 10 to the minus 8, Ka3 is 10 to the minus 13, 2 less, right? So that's why this is. Similarly, that is, and for phosphoric acid, I was saying that previously, as 3PO4, it has 3 hydrogen, that's why it has a 3 acid dissociation constant. Okay. So now some examples are here. You can see that. Okay, NS3, these NS2, these has these much. They all are weak, right? 10 to the minus 5, 10 to the minus 4. They are less than 1, way less than 1. That's why they all are the weak bases. Ammonia, right? C6H5, this ammonia and this C6H5 NS2. These all the NS2OH. These all are weak base. So this is for today, this is for this video. We will do the remaining on the next videos, like the, for example, we will continue here Lewis acid base theory, and then we have a couple of more videos and we will complete that. Okay, so ionization constant pKa, we will see that the pKa1, what is that, and pKa2, and everything we will discuss, and after these few slides we will do the in the next case. Thank you so much.